So recapping the start of chromatography, there are 3 types of chromatography. There's paper, thin layer, and column chromatography. I'm going to talk about each one individually. And basically it takes advantage of the strengths of the intermolecular interactions or intermolecular forces, and it separates them based off of the attractive forces. There are 2 components for all chromatographies. One's the mobile phase, and one's the stationary phase. Obviously, the mobile phase, those ones, it moves. The stationary phase stays put, okay? Stationary phase is always going to be a solid or a liquid attached to a solid that has like a solid backing. And the thin layer chromatography is specifically like that one we're talking about, where it's like the liquid is up against a solid backing, and you'll see that also in the Pivot Lab. Hopefully you'll start that over the weekend. So basics of here, and the diagram up here is showing you paper chromatography, which you may have done last year in Chem 1, where they separate like ink dyes, put them on the paper and the ink dye separates. But as you can see, you start over here with like one origin particular dot here, and then it separates into components. So you have the blue, the purple, the red. Started out with like black ink dye here, separating into 3 different components of that particular substance. Okay, these are mixtures. They have more than one thing in them, and you're separating the mixtures into their individual components using interparticle attractions, molecular interactions in order to separate them. So that goes well with, of course, talking about IMFs, because we've been talking about those a lot lately. All right, so paper chromatography, the stationary phase is usually cellulose paper, which is also basically filter paper that you would use in like gravimetric analysis, same idea there. Cellulose, I don't know if you remember from biology, it is a polysaccharide. It is found in plant cell walls. That's probably the easiest example there. But what is significant about cellulose, it has lots of hydroxyl groups on it. And hydroxyl groups are not hydroxide, not the base hydroxide ion, but they are OH groups that are on the outside. They're functional groups attached to the main carbon molecule. Cellulose is an organic molecule, it's a large molecule, but around the edges of the cellulose there are lots of hydroxyl groups, and we know OH groups allows for what? Hydrogen bonding. So this is a polar molecule with lots of ability to do hydrogen bonding. Okay? The molecules can have a greater affinity for the paper or for the solvent, so greater affinity or attractiveness to the solvent, attractiveness to the paper itself. Okay, if the molecule is attracted to the solvent, it's going to travel with the solvent and go up to the paper. If the solvent has a low attraction to the solvent, it's going to stay more attracted to the paper and just like sit on the paper and come out of solution. Okay, and be deposited on the paper. And the relative attraction that each component of the solution has for the mobile phase solvent will allow you to separate each of the solids in the mixture. Now the one main calculation you have to do here is called the retention factor. So I put this chart in your notes already. Retention factor is known as RF, and it is basically the distance traveled by the component divided by the distance traveled by the solvent. So you have to have those 2 data points. Solvent front line versus where the individual component stopped at. Now sometimes it becomes an issue though, because it's not usually this nice little finite tiny circle here where you can go right to the middle of it, very easily measured. Sometimes it's a big like dot, big oval dot, as seen in this upper picture here. And if it's like the big oval dot, or if it's a big smear where, it's not just one little tiny point on the paper, then you have to do some estimating or averaging. And here, the dye zone, where it's looking at this blue oval, you can go like straight to the middle and try to estimate it there. Or, as you can see up here, what they're doing is they're measuring the top of the component, the bottom of the component, and then taking an average of that. Okay? So, in order to get the center, they do the A plus B divided by 2 and then divide it by the solvent front. And the solvent front is going to be D, this part right here, wherever the solvent travels to. Question?
What does the distance traveled say about the component?
It's not, the distance, you mean for the actual component itself? It's just a way of separating them. So the retention factor itself is just a measurable tool to see the separated components. And the retention factors should be the same for a given solvent and a particular mixture. In various, trials, they should be the same. But really, it's a very, I would say, even though it's a numerical value, it is sort of just one little data point, because unless you have a baseline and you have something to compare to, all it's telling you is, the one that travels the furthest is more attracted to the solvent, the one that doesn't travel as far is more attracted to the paper. So you can determine the polarity, because if your solvent is nonpolar and your paper is polar, the one traveling farthest with the solvent, that tells you polarity, that one's the most nonpolar of the things in the mixture. The one that doesn't travel as far and stays more attracted to the paper will be polar, or be the most polar of the things in the mixture. So it's kind of more of a relative estimation here, unless you have a baseline and something to compare to. Okay? So yeah, it's really, I'd say it's only one piece of evidence in trying to identify components in a mixture, especially if you're working with unknowns. And you definitely need to have baseline knowns in order to try to compare it to. So for example, this one was actually on the 2017 FRQ test, part of the exam. And I would say, if I'm a predicting person, that the chromatography FRQ, pops up like every 4 to 5 years. So it may pop up this year as being part of the FRQ. And nobody had seen one like this in a very long time, so it was kind of a surprise in the 2017 test. But this is kind of like the question you would see on an AP exam. So here you're looking at nonpolar solvent, telling you right there, okay? Chromatography chambers, you have a baseline set here of dye A, B, and C, and then you have an unknown over here to work off of the baseline from. So other context clues you need to pick up on as you're reading the scenario. This is paper chromatography. The student has samples of 3 pure dyes and an unknown sample. The student prepares the chromatography chambers above and then indicates the position on the chromatography paper, which they tell you right here is a polar material. And they also tell you right there that it's a nonpolar solvent, so you should be looking at the polarity there. Developed in the chromatograms shown over to the right. Now you have your data over on the right. So you can start answering the questions. Which dye, A, B, or C, is the least polar? Justify your answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. Okay, so if we're looking there on the right hand, which one is the least polar? Or I would say, which one is the most non-polar? Because that's the same thing, right? So out of those, which one would be? C, right? Because they tell us the solvent is non-polar, right? So the one that's going to travel the farthest with the nonpolar solvent should be the most nonpolar, right? So here C, and you would say something along the lines of the dye C is the least polar because it was more attracted and traveled farther with the nonpolar solvent than dye A or B, right? Because it says to talk about the interactions between the dyes and the solvent or the dyes and the paper, so you need to make sure that you get that in there in your explanation. All right, dye C is the least polar because it traveled the farthest, being strongly attracted to the nonpolar solvent, or dye C is the least polar because it traveled the farthest, being least attracted to the polar chromatogram paper. So you could state it either way. I believe I did take this directly off of the scoring guidelines so you could see exactly how they phrased it. So take a moment to look at that, and then when you get done, go ahead and move on to the next question, or B, or in the next part of the FRQ. Which dye is present in the unknown sample? Looking here at B, I've heard some people say, yeah, it's A. I agree with you, it is A. Okay, I'm going to go with A here. But now we have to justify our answer. And how can we justify our answer? We use the retention factor idea. We can estimate it. Because if you look here, the solvent front up here from the origin, dye A is about what? Approximately halfway. So that's 0.5, right? If it traveled the whole way, it would be 1. But since it went about halfway, okay, that's going to be about 0.5. And if you look over here at the unknown, and its solvent front isn't as far from its origin here, and you can see it traveled also towards the middle of the solvent there. And that would also be approximately halfway, or 0.5, right? So you could look at it and you could state it that way, like it's got to be dye A because it, you know, traveled to about halfway up the solvent front, even though they're different distances for the baseline and the unknown. The retention factor, you know, it going up about halfway is approximately the same. So these were the ones that they wrote in the scoring guidelines. Dye A is present in the unknown sample. Made that declaration. Most of you got that part. The unknown sample traveled to approximately halfway between the origin and the solvent front, like dye A. Or both dye A and the unknown have an RF retention factors that are approximately 0.5. They would have accepted either of those answers. Even though you don't have like actual measurements there, you could make up measurements if you wanted to. Like if you wanted to say this is, you know, 10 centimeters right here, then you could say that this is about halfway, would be about 5 centimeters, and that's how you could do 5 over 10 gives you 0.5, right? I know that doesn't look very good, sorry. Let me rewrite that. So if we decided that was 10 centimeters, we can make up our own numbers. This is 5 centimeters. That would be 5 over 10, which is 0.5. Here, you know, noticing it's not going up exactly, and you could probably estimate this, I don't know, like 7.5, and then this is halfway between that, okay? You can make your own numbers to do that, or you could just eyeball it and talk about how it traveled about halfway, and about halfway is 0.5 of the travel distance if you're doing retention factors. Okay, this is, like I said, directly from the 2017 FRQ. And you're always, you know, just to point out, on the AP Classroom website, they do have prior FRQ years up there. And also on my exam review, recommended exam review Google Doc, I provide links to prior FRQs that you could go look at. Now, some of them, of course, won't make a whole lot of sense right now because you haven't been exposed to that material, but you know, towards April, when you're starting to go back to studying comprehensively, that would be a good place to go. Or you could go to the topics one under the exam review folder. There's a topics sheet, and you could look up topic 3.9 and see if there's any example problems there to do. All right, so now let's talk about thin layer chromatography. Thin layer is what you're going to see in the Pivot Lab, and they use a UV light. It's kind of nice the way they have it set up. Like I said, I probably couldn't set it up as well as they do for us to do in the wet lab over here. But thin layer chromatography, basically the stationary phase is a plate with a silica gel. And the silica gel, I tried to put a structural drawing here on the left for you so you could see. The silica gel, as noted, is polar, and you can see it has a ton of these hydroxyl groups, just like the cellulose paper. So that means the silica gel is polar. Okay? And they put the solvent there, and the mobile phase is going to be liquid or a gas. Most of the time it's liquid. I say most of the ones I've seen, they're liquid, although you can have it work with a gas, being exposed to a gas. The sample spot, very similar to paper chromatography. It's a gel, not the paper, and it's backed by, a solid plate. And it will go up the plate and separate your components into the separate, based off of the polarity too. So usually if the plate in the silica part is polar, that you would use a less polar solvent. It doesn't have to be completely non-polar, but you could use something that's less polar, like diethyl ether, or some of the esters. You could use acetone. They're still in slightly polar category, but definitely considerably less polar than the silica gel. All right. So here's a good example. Explain why the P travels farther along the plate than the SM when acetone is used as a solvent. And I put the structural picture of acetone so you can see. And if you're not familiar with the way that organic draws it with the lines, basically this is the stick figure way. This is really a carbon here in the middle. That oxygen has 2 dots around it, so and it's double bonded. So it does have the 4 bonds, which would be 8 electrons, so it is satisfied in the octet there. But you'll notice the one polar group here, dipole moment would go this way towards the oxygen. So this part is going to be the slightly negative part, and these would be slightly positive ends. Okay, but it is a 3-carbon chain, so that one oxygen group in the middle makes it slightly polar. It's definitely not as polar as the silica gel with all those OH groups, or as polar as water would be. So if we're looking here, we have our starting material. And I don't know if you can see this, but you have a benzene ring. This is actually an OH group. Here, I'll write it in darker. This is OH off of the benzene ring here. And down here, this is a nitro group, NO2 group. Okay? And the OH group definitely makes that one, got some polarity there. NO2, though, on the end with the other 2 oxygens and nitrogen, should always spot those kind of groups because they also increase the polarity. Now the benzene ring, just hydrocarbons, so that part obviously would be more non-polar. Now if we look at the product over here, the way this is written is, I think that's OCH, is that a 2 there? I don't know if it's better on yours. OCH?
I don't know.
OCH 0.
Oh, 0? Okay,
I
then
don't know. Is that even possible?
OCH, and then down here is still the NO2. So really where the changes occurring, they're occurring at this segment and this segment of our molecule during the reaction. And then figuring out how much of each component, like seeing where they are in their starting material versus the product. Oh, they added sodium hydroxide and this carbon bromide organic molecule there. Now, in comparison here, explain why the P travels farther than the SM, the starting material with the acetone. Why would the P travel farther?
The solvent. Wait, it's the solvent polar and non-polar.
What did we say about acetone? Is this polar or
Slightly-
non-polar?
Slightly polar.
This is slightly polar, right?
Okay.
Slightly polar. And out of these two, which have the differences in having OH on the starting material and then OCH on the product material, which one of those is going to be less polar?
OCH.
The OCH is going to be less polar. So, because the O is attached to the benzene ring and then the C is attached to the O. So basically, the way that that combined, now you don't have hydrogen bonding anymore because the O is attached to the benzene ring and the O is attached to the C then. So that separates the idea of being able to do hydrogen bonding. So definitely less polar in the product. So because acetone is slightly polar and the product is slightly polar,
It traveled further in the solvent.
it's going to have more like interactions. The IMFs are going to be more similar, so they're going to stay more attracted to one another. Whereas the starting material has that OH group, which is more polar, so it's going to not travel as far and also be probably more attracted to the silica gel, the stationary phase, than the solvent. So as you can see, it doesn't travel as far. So you do have some different features here in explaining these. Let's see what put here. SF has OH groups capable of hydrogen bonding, which will attract more strongly to the silica gel. P is polar with only dipole-dipole interactions that would be more strongly attracted to the acetone. And the acetone, being slightly polar, is only going to have up to dipole-dipole interactions as well. So they're more similar. The attractive forces are, the more attractive they'll be to each other. And as you can see, they'll travel respectively to the ones they're more attracted to. Now for column chromatography. In column chromatography, they use like a big burette type setup. Okay. There's a stationary phase that has the silica gel or alumina, which is considered to be polar substance. Okay. The mobile phase solvent is known as the eluent, I think. Eluent. Took me a moment to get that back in my head. Because the process of washing a compound through the column using the solvent is known as elution. So you also have in here a couple other components down here by the valve. There's some wool, okay, and to make sure that like the gel doesn't like go through and eventually wash down too much. They also put some sand in there too, and the absorbent alumina, which is also silica, could be silica gel, highly polar. And then basically you have your sample that you're trying to separate. And you put the, because the gel's already in there, and then they put the solvent from the top to begin the elution process. And as it's washing down, the one that's more attracted to the solvent is going to go through the burette, and then you can open the valve and you can drain out that particular component of the mixture. This one is used for larger amounts of stuff, really like separating larger amounts. It's not just to gather data points and information about what's in your mixture. This is really like something they do in industry to separate components. So it's used to separate larger amounts of solution and or mixtures. And able to, then you can, you know, like I said, open the valve and you could take the one component of the mixture and isolate it and have it separated for manufacturing, for industry, for pharmaceutical purposes, whatever. Now let's talk about distillation. Distillation, they ask usually one or two questions about. Distillation separates two liquids with different boiling points. The higher boiling point substance has a lower vapor pressure and stronger IMFs. Oops, let me go back here. So the basic setup here in the picture showing you have the distilling flask which has your mixture in it. And then you have your heat source underneath it. You can, you know, use a Bunsen burner, hot plate, depending upon how high the boiling points are. And this one's showing a simple distillation, has goes straight up. Once the one with the lower boiling point, which has weaker forces, starts to vaporize, it goes up, and then it's going to come down into the condenser. Now what you should notice about the condenser is there's an inner tube and then the outer tube. The inner tube is where the newly vaporized gas is going to turn back into a liquid. The outer tube is where you're attaching it to a water source here, and you're putting through colder water. That's what causes it to reduce the temperature, so it will change back into a liquid. And it changes back into a liquid in the condensing tube, condensation, hence the name condensing tube or condenser, and then it comes out the other end and you collect it in a flask as a liquid. The one with the higher boiling point will stay in the distilling flask, and the one with the lower boiling point is going to come out the other end through the condenser. So stronger IMFs, going to have lower vapor pressures, have higher boiling points, going to be most likely in the distilling flask. The one that's got weaker forces, the lower boiling point and higher vapor pressure, that's the one that goes out through the condenser. Now there's simple versus fractional distillation. And like I said, I showed you the apparatus for simple where it just went straight up and went into the condenser. But for fractional distillation, which is one that they use more, I'd say, in industry, because in a lot of cases when you're separating large amounts of mixture of stuff, the boiling points are going to be closer together. And if you send it just up the simple distillation, in likelihood you're not going to get as pure of a substance coming out the other end. But they add this fractional column here, and it kind of like winds around. And what happens in that column is, as it's going up, the one that's truly has the higher vapor pressure and the lower boiling point actually makes it to the top and gets into the condensing tube, comes out first. And then the ones that are kind of in between that are close to that one, but not exactly, a little bit lower, they will, you know, you'll have to heat it a little bit more to get those to come out and so forth. So they re-vaporize several times, leading to better purification. So I put this chart in here too to give you the distinguishing factors between fractional and simple. Fractional separating the process for separating the mixture into its part. Simple, two liquids can be, you know, by different boiling points separated. Boiling point, the fractional distillation, separate mixture, they're close to each other, those boiling points. And it's used more for crude to refining, like they use it in manufacturing various types of fuels, because the fuels have different boiling points, and you basically take that crude oil and they undergo the distillation process to separate it and refine it. Simple would be something like you could use it for desalinization, where you're just evaporating the water out from the salt. You can do that. But as you can see, it's going to take a lot of energy to do that. So cost benefit wise, sure, we could heat up seawater and get pure water that way, but obviously it would take a lot of heat, which would take a lot of energy source in order to do that. So cost benefit wise, it's not of that great a value. Now there's a video here that goes over the distillation curves and along with the heating curve, and shows you the difference between fractional and simple if you want to take a look at that. He does a good job talking about it, but I don't know if like it's real necessary to make everybody watch that. The last one here is evaporation. Evaporation, basically you're just trying to recover the solid, because you heat up the solution, whatever's the solvent, a likelihood probably water, it's just going to evaporate out. You're not collecting it, and then what's left behind in the beaker or in the container that you heated it in, you're going to have the crystals there. So you're recovering the solid if you're doing evaporation, whereas you use the distillation apparatus to help you collect the liquid product if you were wanting, like we wanted to separate seawater and just get the salt, you'd probably use evaporation. But if you wanted to separate salt water and seawater and keep the purified water, you would want to use the distillation apparatus to do that.